This diagram illustrates how power domain islands affect the placement of MemoryBIST controllers in a design. The outer block, labeled Block A, contains a nested power domain Block B, which itself includes two subblocks, Block C and Block D. Each memory instance, Mem0, Mem1, Mem3, and Mem4, is associated with a specific power domain. For example, Mem0 is in PD Blue 2 within Block C, while Mem1 is in PD Blue 3 within Block D. These memories are isolated into separate power domain islands due to their distinct power domains, even though they reside within the same parent block, B. This diagram illustrates how Tessent MemoryBIST determines physical clustering of memory instances based on their placement within the design. The tool defines a bounding rectangle that encloses all memory instances in the current design and calculates the diagonal of this rectangle as a reference for cluster sizing. The physical cluster size is then determined by a ratio of this total diagonal, controlled by the minus physical cluster size ratio parameter. This diagram illustrates the integration of MemoryBIST logic into a memory interface, focusing on the bypass and observation registers that enable testability. The functional data path, shown in green, carries normal operation signals such as address, data, and control inputs to the memory. During scan testing, the test-only paths, shown in black, redirect these signals through dedicated bypass and observation flops. These include MemoryBIST flops, scan bypass flops, and scan observation flops, which allow test patterns to be applied and responses captured without interfering with normal operation. The design includes exclusive OR gates to manage signal selection between functional and test modes, controlled by signals like mem bypass enable and scan shift enable. A key consideration is the relationship between the number of bypass registers, M, and the width of the data bus, N. If M is less than N, there's a risk of undetectable faults due to input correlation in the functional logic. When M equals N, timing paths to bypass registers mirror those to memory data, minimizing skew. The physical data map and comparators are used to validate test results, while persistent gates like BIST input select help maintain test mode integrity. This architecture balances area efficiency with test coverage and timing performance. This diagram illustrates the data flow and control structure of a MemoryBIST controller interacting with multiple memory interfaces. The BIST controller generates test patterns and manages the testing sequence, using signals like address, write data, and CHK, enabled to drive memory operations. These signals are routed through expand blocks to accommodate different memory interface widths, ensuring compatibility across various memory types such as Mem0 through Mem-K. Each memory interface includes address and data mapping logic, which translates the BIST controller's signals into the appropriate format for the target memory. The expect data signal from the step counter is compared against actual output via a comparator, enabling error detection during testing. The Go ID signal, derived from BIST Go, initiates the test sequence and controls the step counter, which tracks the current test phase. The pipeline stages shown in the figure, particularly around the comparators, reflect how MemoryBIST handles timing and synchronization. These stages help manage delays introduced by complex memory hierarchies and ensure reliable comparison of expected versus actual data. This architecture supports efficient, automated memory testing while maintaining flexibility across diverse memory configurations. This diagram illustrates the architecture of a MemoryBIST system, showing how a central BIST controller interacts with multiple memory interfaces. The controller generates address, write data, and expected data signals, which are routed through pipeline stages to each memory interface. These interfaces include address and data mapping logic, as well as expansion circuits that adapt the test patterns for specific memory configurations. Each memory interface connects to a corresponding memory block, such as Mem0 or Mem-K, enabling parallel testing across multiple memories. This diagram illustrates the architecture of a MemoryBIST system using a shared bus interface, where multiple memory instances are tested through a centralized BIST controller. The controller manages test operations by sending address and write data to individual memory interfaces, labeled as Memory Interface 0 through Memory Interface K. Each interface includes components like address mapping, data mapping, and expansion logic to adapt the controller's signals to the specific memory's requirements. This figure illustrates the config data browser interface used to explore the hierarchical structure of a DFT specification within Tessent Visualizer. The left panel displays a tree-like hierarchy starting from the top-level DFT specification with expandable nodes such as Top Network, RTI Cells, RT-Scan DFT Logic, MemoryBIST, and MemoryBIST. By clicking the arrow icons next to these wrappers, users can drill down into subcomponents, revealing deeper levels of the test configuration. This hierarchical navigation allows engineers to inspect and modify specific aspects of the DFT setup, such as MemoryBIST controllers and their associated interfaces. This figure illustrates the hierarchical configuration of a DFT specification using the Tessent Visualizer tool, specifically focusing on the MemoryBIST controller setup. The left pane shows a tree structure where the user navigates through various wrappers such as DFT Specification, MemoryBIST, and Controller C1, down to individual test steps like Memory Interface M3. This hierarchy allows engineers to define and organize test sequences for memory built-in self-test, BIST, operations. The right pane displays configurable parameters for the selected step, such as memory library name, repair group name, and data bits per bypass, which control how the BIST logic behaves during testing. These settings are critical for tailoring the test to specific memory instances and ensuring accurate fault detection. By selecting a step in the hierarchy, engineers can modify its properties directly, enabling precise control over the test flow and diagnostic capabilities. The interface supports dynamic editing, allowing users to add new steps under a controller, as described in the accompanying text. This capability is essential for customizing test sequences to meet design-specific requirements. The visual representation emphasizes the relationship between structural elements and their associated configuration values, providing a clear workflow for planning and inserting MemoryBIST into a DFT specification. This figure illustrates the process of adding a new test step within the config data browser of the Tessent Visualizer tool, specifically for configuring a MemoryBIST controller. The user is working within the DFT specification hierarchy, focusing on the controller C1 instance under the MemoryBIST wrapper. The context menu shows that the user has right-clicked on a step node labeled ST to insert a new configuration element. The highlighted option, Add Wrapper as a Child, indicates the action of embedding a new wrapper beneath the selected step, which is essential for building structured test sequences in DFT specifications. The right panel displays configuration properties such as Clock Domain Label Set to Clock, which defines the timing domain for the test operation. This reflects how engineers define and organize test steps with specific parameters to ensure proper MemoryBIST functionality. By using this interface, users can hierarchically build complex test plans, ensuring each step is properly linked to its parent and configured with necessary attributes. This capability supports precise control over test execution flow and timing, critical for reliable memory testing in integrated circuits. This figure illustrates the process of adding a new test step within the Tessent MemoryBIST tool, specifically during the configuration of a DFT specification. The dialog box shown is used to insert a wrapper for a test step, which is a critical part of defining the test sequence for memory built-in self-test, MemoryBIST. The user selects Step from the drop-down menu, indicating that this wrapper will represent a procedural step in the test flow. The Apply and Cancel buttons allow the user to confirm or discard the action. This operation is typically performed when building a hierarchical test plan, where each step may correspond to a specific memory test pattern or control sequence. By adding such steps, engineers can define the order and parameters of memory tests, ensuring comprehensive coverage and proper integration with the overall DFT strategy. This interface supports structured test planning by enabling users to modularize test procedures into manageable steps. Each step can later be configured with specific settings such as test patterns, timing, or scan chain controls, contributing to a robust and scalable MemoryBIST implementation. This figure illustrates the process of reorganizing a MemoryBIST test configuration using the config data browser in Tessent Visualizer. The engineer is modifying a DFT specification by moving a memory interface component, specifically Memory Interface M3, from one test step to another. This operation leverages the cut-and-paste functionality within the tool, allowing for flexible test flow customization without manually redefining parameters. This image shows the config data browser in Tessent Visualizer, where a DFT specification is being edited. The left panel displays the hierarchical structure of the DFT configuration, with MemoryBIST components and their associated interfaces highlighted. The selected node, Memory Interface M3, indicates the current focus for configuration. On the right, the filter table lists configuration parameters such as memory library name and instance name, which are critical for defining how the BIST logic interacts with the design. The error message at the bottom reveals a validation issue. Some loaded modules use the design name top and ID RTL, which conflicts with DFT component insertion rules. This prevents proper DFT integration. The red circle in the top left corner highlights the validate button, suggesting that clicking it triggers the error check. Engineers must resolve naming conflicts before proceeding with DFT insertion to ensure correct test pattern generation and fault coverage.